Okay, so it's great to be here to be able to give you some lectures on progress in multi-loop calculations. I wasn't the original speaker for this lecture series. It was my colleague, but he's applying for a green card in the US, and so he's been advised not to leave the country for a little while. So, so he got me instead. So I've worked on some of this in the past, but I've been doing a little more formal things more recently. So I might not tell you everything like totally up to date in the very last word on it, but that's okay. This stuff gets very technical. I'll get to the very end of it. It will still be fine, I think. Um, I'd really like you to encourage you to interrupt me a lot, and that way we can have a dialogue, and I can see that I'm getting at the right level and so on. So please, just raise your hand and ask a question if there's anything you don't understand. Because if you don't, I might start asking you questions instead. So I'm going to do this pretty much all on the blackboard, I think, except that I want to give one motivational slide over here. At least it's motivation for me, at least when I was closer to this. But this shows a remarkable set of measurements that's been made by the ATLAS collaboration, and there are similar measurements made by CMS as well, which is the kind of precision that's available at the energy frontier at the world's most energetic particle collider, the Large Hadron Collider. And of course, ATLAS and CMS are the two detectors for high transverse momentum, short distance physics. And you can see that they have measured these cross sections that range from, well, we can forget about the PP total cross section. That's a little different kind of physics, but starting with the W there at I think 10 to the 5 picobarns down to sub-picobarns. So they've measured these cross sections over 5 orders of magnitude in size, and they're getting pretty good, incredible precision on the highest cross sections, and then there's statistical issues with some of the lowest ones. These are from 2019. That was the latest data I could find, a summary plot. Maybe people know if there are better ones, but you can see that all these measurements span a wide range. If you have really good eyes, they'll tell you what theory they compared to here. And it ranges from W and Z production and also Higgs production to more complicated events, classes of processes. And since it's hard to see error bars on a log scale, you should really go over here and look at the ratio between data to theory. And for the simple things with one body in the final state, and also for TT bar, the precision is very good. And if you're a theorist, you kind of want to focus on the things that are in the gray bands. That's the uncertainty of the theoretical prediction. And for the stuff at the top, it's a few percent. One tick here is 10%, but it's below one tick. It's like a few percent for W's and Z's. TT bar is below 10% for sure. Some of these other ones are small, but then you can see a lot of these down near the bottom there have fairly wide theoretical uncertainties. For now, it's not a huge deal because the experimental uncertainties are mostly a bit larger, but as you go into the high Lumi run of the LHC, the statistics on these events are going to become much better, and these will shrink. So does anybody have an idea why these error bars are larger than some of the ones above? What is it correlated with? You see how many bodies there are in the final state here, down here? There's like 3 or more. And the ones above are generally all 2-body. So these have not really been completed at the multi-loop level, at next to leading order. They're only known to NLO because the technology for doing the 2-loop processes with the many scales that come in when you have a 2 goes to 3 process is not really there yet. Whereas most of the 2-body ones have been done at NNLO. And some of that advance is made possible by, in large part, by studying the properties of the loop integrals that you get at 2 loops. There's also a lot of work that has to be done on other aspects. But I have a big motivation to keep up with the experimentalists in keeping the precision of the predictions as under control as possible. So there's one kind of final state that isn't very well represented in this plot. Can anybody say what it is? It's not exactly a particle, but it's a collection of hadrons that are collimated and go in a given direction. So that's a jet, right? So they didn't show, multi-jets. There's one J buried in there. But all of these processes, they also come along with jets, and they're, as well as the pure jet events. That just wasn't the focus of this. This is sort of the focus on electroweak processes. But they also have measured everything with jets, too. Do precision physics with jets, as well as this stuff at high precision. And also combine it with a lot of ideas about resummation and Monte Carlos that Emmanuel is going to talk about in the next set of lectures. So here I'm going to just tell you briefly what I'm going to focus on and what I'm not going to talk so much about. So it says multi-loop here, but of course I'm going to start with 1 loop and then we'll go on to 2 loops later, and that'll be, except for the end, most of it. So I'm going to focus on QCD corrections, because those are generally the largest at the LHC, because alpha S is bigger than alpha weak. This is about 1/10 at the 100 GeV scale. This is about 1/10, and this is maybe 1/40. Now, sometimes there are regions where you get very large transverse momenta, and you might get large logarithms, and then this isn't really quite so true, and then it's to do the ultra-weak corrections as well. But anyway, I'm just going to focus on QCD here. And although I'll say a few words about real radiation, I'm going to mostly focus on virtual, because after all, I was assigned to do loops. And more than and within loops, I'm going to focus on the thing that's the real bottleneck, which is the loop integrals. There's other aspects to doing the loops, which is to sort of you can also discuss loops and talk about the structure of the loop integrands that you get before you do the loop integrals. And you can use methods like unitarity, but I'm going to focus more on the loop integrals in these lectures. And because I've been doing some other things recently, I'm going to expose you to a little bit of that at the end as time permits. And we're going to change the theory from QCD to another theory called planar n equals 4 Super Yang-Mills theory, because it's fun. because the state of the art in a lot of QCD is 2 to 3 loops, and we can go to 8 loops in this theory. So we can find in some cases, for special processes, lots of symmetries and so on that allow us to push very far into the loop expansion. Any questions about any of that? So let's start off not at 1 loop, but just at tree level, just to get started. So we'll just, I want to just lay out the kinds of things you need to compute to go to next to leading order. And we'll just talk about one case, which is not covered there, but it's the case of jet production, inclusive jet or dijet. So the way we think about high transverse momentum production at a hadron collider, and some of this may also be reviewed by George Sturman later on, maybe by Emanuela too, I don't know, is that at very high transverse momenta, we think of these protons coming in as big fat objects. They have scales about a Fermi in radius, but we're going to be looking at 1,000th of a Fermi or something. We're going to be looking at scales that are much shorter than these two overlapping protons, which are about the same size. Anyway, these protons have these hard constituents in them that we call partons, which are quarks and gluons. And if we're at very large transverse momentum, that's conjugate to very small distance scales. And so we might pick up, and here's some partons in one proton, and here's some in the other. And so the odds are just 2 of these are going to collide at one time. And so they're going to make our high momentum collision. And these guys are going to be spectators. And the first approximation, we're just going to ignore them. And we're going to be working in the QCD improved parton model. And that just means we draw 1 parton from each proton for a collision. So here we have if this is proton A and this is proton B, we have a gluon distribution for XA and a gluon distribution for XB. And then we have a sigma hat that for glue to something that acts at SAB, which is XAXB times the total center of mass of the LHC. And then we want to compute these short distance cross sections to higher orders in the alpha S. Any questions about that? So at lowest order, we have processes where gluons can scatter into more gluons, or gluons can scatter into QQ bar, or quarks can scatter off of gluons, or antiquarks, or quark-quark, or quark-antiquark scattering, stuff like that. So you have a number of different processes, but the basic idea is you draw these 2 partons of the appropriate flavor, gluons or quarks, and at leading order you do a 2 goes to 2 matrix element. So this blob I'm drawing, if I don't put a hole in it, it means it's tree level. And you could write it down as a sum over all the Feynman diagrams. Excuse the artwork, my gluons are really lousy. So there would be 4 Feynman diagrams in this case. And the leading order cross-section is really d sigma hat in terms of the two-body phase space is a sum, maybe I should put sum prime over color and helicity of this amplitude shown in this blob, magnitude squared. And of course, you really need to average over initial states. So you need to divide by the number of initial colors, like n squared minus 1, and the number of initial helicities, 2, and do this square. And that's the leading order cross-section. And we can also write it schematically like this. To indicate, this indicates a interference diagram. So it indicates an amplitude times a conjugate amplitude. So let's also just write this as the same sum over C and H of A0 squared. So that's the leading order cross-section for producing gluons, but we don't see gluons at the LHC. We see jets. So there should also be some kind of a measurement function, which I'll draw a little bit like this, that defines a jet. I'm not going to go into the details of jet algorithms. The one thing you need to know about jet algorithms, or about the things that you can predict in QCD without introducing more non-perturbative aspects, is infrared safety. So you might have an observable. For any infrared safe observable, it should be defined on states of multiple numbers of partons. Okay, it has to be defined for a general number of partons. And it also has to have the property that if you put two partons in here, and if these two partons are parallel to each other or collinear, this parallel sign indicates that they're collinear, then it has to go smoothly into the same observable, which has one fewer parton in it, where Kp is the sum of Ka plus Kb. This is called collinear safety. There's also another one, which is that if you have somewhere in here some soft momentum and you send that to 0, then you should get back the same endpoint thing where you delete the soft momentum, and that is soft safety. So if you put that together, that's called infrared, or sometimes infrared collinear safe observables. And what you're trying to do here is you're trying to construct things that are insensitive to long distances, because you can have a process where you add a very low wavelength, long distance gluon, or you can have a process where one gluon splits into two collinear gluons. But this splitting behavior, if these become parallel, this becomes very large, and it can happen at very long distances. At long distances, the strong coupling gets very strong. We can't use perturbation theory anymore. So to focus on short distances and not non-perturbative physics, we impose these two criteria. Any questions about that? And at the level we're going to discuss in these lectures, a jet is a way of making sure that that happens. What it does is it tends to cluster partons together, but it adds up the momenta in such a way to satisfy this. So if two partons are very collinear, they will generally end up in the same jet. And the rule is that the momentum of this cluster, after you cluster them, is more or less the sum of the momenta of the two partons, so that that momentum goes smoothly in this limit over to this momentum here. Now, this is not even an issue at leading order. That is to say, at leading order, jets are very, very simple, way too simple. One jet is actually equal to one parton. There's another parton in this 2 goes to 2 process, but it goes to the detector. Never make it into the same jet, because jets are defined to be fairly collimated. But this statement that one jet equals one parton will soon be modified as we go to next to leading order. Maybe I should also just, let's just count powers of G here. So these amplitudes have 2 GS's in them, but we're going to take the square of them. So the cross section we're talking about has 2 GS's, and alpha S is GS squared over 4 pi, and we can ignore this in counting the GS's. So this is alpha S squared. So we're doing leading order here, and for this quantity, leading order means order alpha S squared. And there are various ways to organize these amplitudes, but we're not going to focus on that too much right now. So now I'm going to go on to next to leading order, unless there are any questions about leading order. Any questions? It's okay to ask. Okay, so NLO means order alpha S cubed. And that means GS to the 6th, which can be written as 2 ways, GS to the 4th times GS squared, or GS cubed times GS cubed. Well, you can partition it other ways, but they don't correspond to decomposition into amplitudes for this case. So this decomposition corresponds to the virtual corrections. So, well, we're going to diagrammatically, we want to construct an interference like this. So we take the same process, 2 goes to 2. Oh, and I'm going to, well, I already did it over here, but just I'm going to ignore the quarks. You can put them in there, and everything's more or less the same, except you don't have soft quark divergences, whereas you have soft gluon divergences. So anyway, what this interference means is it means that we write down A1 times A0 dagger, the complex conjugate of the tree. Everything on the right-hand side should be complex conjugated. Just like here, we had A0, the leading order amplitude, multiplied by the conjugate one, which is the square. Here, because we're expanding in perturbation theory, this term is not exactly the square. It's the it's really the extracted from the total square, this piece, which is twice the real part of A1 A0 dagger. So that's what you need for the virtual corrections. And as usual, there's an implicit sum prime over color and helicity. So this would include this box graph with a gluon going around the loop. You could also send quarks around the loop and so on. And then there would be other diagrams that would have fewer propagators going around the loop. For example, this triangle, bubbles, things like that. But these amplitudes are all divergent in 4 dimensions. So we introduce dimensional regularization with d equals 4 minus 2 epsilon. And you have, we'll see explicitly this when we do one of these integrals later, but you have regions of integration here where we can pick on any one of these gluons. So suppose that this gluon is soft. Then there will be a 1 over p squared propagator that it blows up as p goes to 0. So that's a soft divergence, virtual soft divergence. But it could also be that this gluon could be become collinear to this leg, this virtual gluon. And then if you think about it, this one will also be collinear. So you'll have a couple propagators that are getting singular in a slightly different way. But there's also collinear divergences when p becomes parallel to momentum 1 or momentum 4. And because there's 2 types of divergences, and they're regulated by dimensional regularization, the typical thing you get in a QCD process at 1 loop is the typical divergence. And it actually always has a negative sign, at least at leading color. But that was the GS to the 4th times GS squared contribution, that is the virtual contribution. We also have real contributions. And again, I'll just, even if you had glue to 3 gluons, you might also have to do everything properly, you'd have to include quark terms like this, and of course, there would be other, contributions, a whole set of other processes to include, but we'll just ignore the quarks again. So we do a Born level amplitude, but now it's not for 2 goes to 2, it's for 2 goes to 3. Glue to 3 gluons, which is the cross-section for producing this, and then you should multiply by the 3-body phase space. And now the problem is that the integral over the 3-body phase space can be singular. So we have a situation where or we can have a situation where two of these gluons are collinear and they enter the same jet. Okay, and then according to the jet algorithm, they produce a trigger. They're integrated over, and but there's a divergence here when these two guys become parallel. This amplitude in this collinear limit factorizes. The long distance structure of this splitting is universal, and at the amplitude level, this thing is called a splitting amplitude. But if we take, and then let's just call it split. But split squared is a splitting probability, the thing that enters the DGLAP equations. If we do everything in helicities, then it will be some kind of polarized splitting function. So these things are universal. They just depend on one variable z, which is the relative momentum fraction between carried by one of the two gluons. But because this has a universal behavior, well, first of all, our jet definition was supposed to be infrared safe. So we end up with more or less a universal integral over this singular part of the phase space. And that produces a 1 over epsilon for the collinear part. But there's an additional soft tail in it, which gives us a plus 1 over epsilon squared. And that ends up canceling the leading behavior of this. Now, there are also some extra minus 1 over epsilon terms here, and there will typically be some pure collinear 1 over, or pure soft 1 over epsilon terms here. So the 1 over epsilon squared terms cancel exactly, but the 1 over epsilon terms do not. So there's a virtual real cancellation, and this is stated as being due to the KLN, Kinoshita-Lee-Naumburg theorem, which was originally formulated for QED with massive electrons and muons and stuff. So it really covered soft things, but when you make, so to deal with the collinear divergences, you make sure that your observable is infrared safe, and then you get these cancellations happening there as well. But the 1 over epsilons don't completely cancel. Anybody know why they don't cancel? So they would cancel if we were doing a problem in jet physics in electron-positron collisions. Right, so they have to be, you have to renormalize the PDFs. Which at some level are certain operator matrix elements, and you have to normalize the operators the right way. But we usually phrase it in a kind of X-space language that the because of this renormalization, there's a term from the leading order splitting kernels that gets convoluted, that's what this means, with the d sigma leading order. So the picture we would draw is that you would have some initial momentum fraction x, and then you would split, and this gluon would be unobserved and not participate in the collision. And then this thing would come into the collision, been degraded by a factor of z, where z is between 0 and 1. And that splitting fraction then has to be, you have to integrate over z and get the factors right and do some convolution integral. And once you do that, then you will subtract off the remaining 1 over epsilon pieces. This isn't meant as like a complete derivation of this, but just heuristically, that takes care of the state singularities whenever you have colored initial states. Like in electron-proton, you have to do it once, and in proton-proton, you have to do it twice, once for each initial parton. So, any questions about that? Yep. Yeah. Yeah, well, it depends on, there are some things that are removed by your jet definition. So the jets allow two things. You might say, okay, I'm going to do a jet at leading order. I'm going to do a leading of a 3-jet cross-section. So that means I've got to establish 3 of these cones separately, okay? And the way the jet algorithms work is that if you move 2 of these guys to become collinear, or say one of them to be very soft, let's do the collinear case. The 2 collinear ones can make 1 jet, but then you've lost this guy. And the point is that when you said it was leading order 2 to 3, you meant that you required there to be 3 jets. So if you lose one at leading order, you're sunk. So it cuts off the phase space to make sure there's no divergences in the 2 goes to 3 process. The jet definitions don't allow partons to become collinear at leading order. Now you could go to next to leading order for 2 goes to 3, and that would similarly involve radiating a 4th parton. And now you'll get the same kinds of divergences, but they'll also be universal. They'll involve the same splitting amplitude, just decorating an amplitude with 1 more hard leg. That's a great question. Any more questions? Yep. You can do inclusive jet, and the graphs that contribute are basically the same as dijet. It's just that in that case, you can integrate over all the variables of the other parton and not care about it at all. Whereas when you do it for dijets, you're specifying where the dijets are, and so you're not doing all the integrals over the other parton. But the structure of the graphs you need and which guys are divergent is more or less the same. Inclusive jet and any other questions? But I should have emphasized, I sort of said it here, but anyway, for the virtual corrections, it's still true that 1 jet equals 1 parton. But of course, those are infinite. They have to be combined with the real ones. And at the real level, you have one jet is 1 or 2 partons. So only at NLO do you start to kind of look inside the jet and ask how energy is distributed within a jet. Before that, it's just 1 parton. There's no dependence on the cone size, or very little. So now we go to N and LO, alpha S to the 4th. We can so one contribution here will be 2 loop amplitudes for glue to glue interfered with the tree. So this will be, this stands for twice the real part of A2, A0 dagger. So this is called doubly virtual, or we could call it VV, because it has 2 virtual loops. But there is a second piece, which is A1 magnitude squared. So these amplitudes here, you can have the same kind of virtual divergences that we talked about here, but now you can do it twice. So you might have a graph like this. So this guy can be soft, but this guy could be even softer. This guy could be collinear, this guy could be even more collinear. And so you are going to get this minus 1 over epsilon squared, but the worst thing you're going to get is 1 over epsilon to the 4th from putting that in. And so the 2-loop answers, these 2-loop amplitudes, you will need to have 1 over epsilon to the 4th terms in the virtuals, 1 over epsilon cubed, all the way to epsilon to the 0. And now for A1, it's a pairing squared. So it used to be you needed to the 1 over epsilon squared terms the 1 over epsilon. But now you need the epsilon to the 1 and the epsilon to 2. That you didn't need at NLO, because when you take this square, it will interfere, this epsilon squared will hit this 1 over epsilon squared and give you something that's finite as epsilon goes to 0. So you need to do these doubly virtual, the 1 loop squared terms, you have to have the 1 loop amplitude to higher orders typically. And I should draw a schematic of that, which is just so that's the doubly, this is all the doubly virtual. Oh good, I can steal this. Now we can do the virtual real. And you'll hate this, but I'm going to just start putting loops in here. So we can, well, maybe that wasn't a good idea because I messed this up by adding extra stuff. But so we have the 2 goes to 3, and that got us a GS cubed for this, but now we can take 1 loop on one side. And so we have the same kind of 1 loop interference we had before, but for 2 goes to 3. And we get minus 1 over epsilon squareds as the worst behavior of the virtual amplitudes for a similar reason. But then you also will get more singularities when you integrate over phase space, like you did in the tree level 2 goes to 3 at NLO. And then finally there will be the double real. So that will come from 2 goes to 4 configurations. So now you set up your jet, but you can still have things like triple 3 gluons going in there. So that is called triple collinear behavior of amplitudes. 1 goes to 3. That's one of the singular regions, but you could also have 2 times the 1 goes to 2 collinear. In other words, you could have 2 of these guys disappear into 1 jet, and then another 2 guys become collinear and disappear into another jet. So that's a separate singular region that you have to take into account. And then you can also have, you can change some of the collinear ones. You can have a single 1 goes to 2 collinear, and then you can have a soft gluon radiated at wide angles that can be picked up by the jet. And then you can have double soft, which have quite complicated color configurations. So this is just to emphasize that there's a wide range of real radiation singularities that you have to account for before you can turn your nice 2-loop amplitudes into something physical. And even after, so this same KLN theorem basically says cancels down the 1 over epsilon of fourths cancel down to about 1 over epsilon squared. But in order to finish the cancellation, you need to worry about things like this, PLO GG convoluted with PLO GG convoluted with this d sigma hat GG to GG, which has a picture like of double collinear splitting before you hit the hard process. Or the one could be on one leg and one on the other. And then you will also have to subtract to finish, this is a 1 over epsilon squared contribution. And then you'll have a 1 over epsilon times the higher order kernel to finish the job, which is, you could heuristically represent it sort of like this, but it is also inclusive, so it might have another gluon on there. Anyway, so there's also a little more complicated set of initial state subtractions you need to do at next to leading order. So any questions about that? I'm really not going to say too much about the real radiation, but I just want to mention that there are various methods to deal with it. And They used to be called subtraction or slicing. So I want to make a small comment that something often called QT subtraction is really a slicing method, just in case you're wondering. But the basic idea is can be sort of illustrated with a simple example, which is E plus E minus to QG Q bar. So this could be the invariant mass of the quark and the gluon, and this could be the invariant mass of the antiquark and the gluon. When you do the integral over the whole phase space, and we could be doing something like NLO 2-jet production in E plus E minus. And this would be the real radiative correction. At leading order, we would just have E plus E minus to QQ bar. And then we would get this at next leading order. And when you look at the differential cross-section for this, it has a singularity over here, which is as SQG goes to 0. So that happens when the quark is parallel to the gluon. And it has another one over here when the antiquark is parallel, or the gluon is parallel to the antiquark. And then over here is one where the gluon is soft. And both of these singularities end up with contributing to the 2-jet production, so they have to be integrated over, and they're divergent. So you either have to you can approximate the real radiated amplitude squared, and then subtract it. And it has to be an approximation that coincides with the leading power behavior here, and also one for here. And then if you can make such an approximation where you can do the integral of the approximation analytically, then you do a, got a little out of order here. You want to calculate some NLO cross-section where, in this example, n is equal to 2. And it's an integral over the n-body phase space, or some n-body phase space of n jets. And roughly, it looks like an n-body phase space over d sigma virtual, because there are some virtual corrections to this amplitude, but they live in the same QQ bar phase space. But then there's this real correction, and this one has to be regulated with epsilon. And then you have a n plus 1 body phase space integrated here. So what you do is you build an approximation, and you rewrite the thing as d sigma v. So the idea is that this approximation has to have two features. It has to approach d sigma r sufficiently well in the singular regions that the remaining integral is finite, and you can set epsilon to 0 afterwards to get a finite answer here. Because if you have to do phase space integrals that are divergent in dim reg, you can do them numerically, but it's extremely hard to get very high precision for the epsilon equals 0 part. So these subtraction methods make it possible to set epsilon to 0 after you remove the divergences and push them somewhere else. And the second feature is that the approximation has to factorize into the same n-body phase space as in the Born process, and then an extra one-dimensional phase space integral, which will include something about the collinear variables going to 0, and also integration, could be an integration over some collinear splitting fraction as well, if it's the collinear terms. So then this one, if it factorizes properly, you do the one-dimensional integral and you find exactly the poles in epsilon that appear in the virtual term. This also includes the collinear terms we talked about before. And then at this point you set epsilon to 0 and you get a finite answer out. This is not to explain to you how it's done, it's just to give you a rough overview. And it just gets worse at NNLO. You have to split things up into virtual, 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 real, 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 reshuffle terms, combine them in a way to make everything finite. Any questions? So do you guys want to take a short break or keep going? Okay, here's one for going. Keep going? Okay. So that was what I wanted to say about the little I wanted to say. Oh, okay, there was one little more add-on, which is that there's sort of, at one loop, subtraction methods have been more popular. So there was Catani-Seymour is a very popular kind of subtraction. There was, even prior to that, there was Friccione-Kuntz-Signer subtractions, and then there's also an antenna subtraction. And that was originally due to David Kossauer, and then groups involving Glover and German implemented it at the next order. So they are a little different. They partition the phase space a little bit differently. So for example, CS is sort of collinear plus half of soft. In other words, when you draw a picture of a hard process and you ask where gluons can be radiated and where you get singularities according to these directions, they're going to be soft singularities, which if things are color connected in the right way would just be between different wedges. But you would also have collinear singularities. And this one, the CS, I think organizes it like this, whereas the antennas do it the other way around. There's sort of soft plus half of collinear. So this is the CS one, and then the antenna for the same kind of configuration here would look, it would be organizing things in different wedges of how the different terms try to match the overall behavior of the amplitude. But since I'm not giving you any details, this is kind of just for and then a number of processes. The first processes to be done at NNLO were ones with color singlets in the final state. So if you have something like PP goes to Higgs plus X, or PP goes to W or Z plus X. And then you could partition phase space according to QT was greater than or equal to a QT cut. So QT is the QT percent. So you ask, you pick a tiny value for this QT cut, and if the momentum of the Higgs, so we're trying to do these at NNLO. And then if the QT is above a certain cut, then we know that we have a Higgs, but something is recoiling against it. So that means it's equivalent to an NLO problem of Higgs plus jet, except we don't really have to apply a jet definition. So that's when QT is greater than QT cut. So for this part, we can then borrow some next leading order code that works, and that might have subtractions in it. But we can slice with respect to QT. And then for the QT less than QT cut, we need to understand the thing that, well, which is resummation in small qt and expanded back out perturbatively, and that predicts the integrals over the small qt region, which we can do analytically, and then add them to the larger qt piece. So this, yeah? Yeah, so the part that's, so this has to be small enough. So it has to be small enough so that the power suppressed terms that you've omitted as QT, and if you've omitted the subleading powers in the factorization, then they're going to appear here. So what you have to do is you have to run your program at different values of QT and look for stability so that the power corrections are suppressed enough. Good question. So this is kind of one way of doing color singlet production at NNLO, and it's a way to do it. But also these antennas have been done and in principle have no restriction on whether it's a color singlet final state, so they were used for jet production. And this is not the end of the story either, just examples. Any other questions about that? Otherwise, we'll assume that all the real radiative stuff is done by somebody else, and we just go on and talk about loop amplitudes from here on. So one loop amplitudes. So in contrast to the two loop case, the integrals have basically been known for a long time. We could almost say forever. So the more recent progress maybe was in going to high multiplicity. Kind of organizing the integrand. For example, using ideas based on unitarity, but they're, or recursive approaches to constructing it. So using some of these more recent things, it's been possible to go in the last 10 or 15 years from a situation where you could basically do about NLO 2 goes to 3. That is 3 jets or 3 in a vector or something like that. Now, 5 or 6 objects in the final state. And it more or less goes off of equations that look something like this. That if you take a scattering amplitude, for example, this one loop glue to glue amplitude, it's convenient to organize it on the outside according to the helicities, which are plus or minus 1 for gluons. And it's useful to think about what would happen if you took the imaginary part in this S12 channel. When you should organize it with respect to color in particular ways, but I'm just not going to go through that. So when you do that, then you get to use the cut rules that say that the discontinuity in a given channel is given by integrating over graphs where you put the lines on shell, but then they basically become tree graphs for the lower tree graphs for processes. So here's HA and HB. And the nice thing in QCD is that a lot of these trees are 0, many more than you might have thought, just given the symmetries of QCD. So there are many tree level zeros. We often use all outgoing helicity convention. In that convention, if we have a quark and say an anti-quark, and then we can have anything else going on over here, this is 0 when they both have the same helicity. That's because if it was a quark, if we crossed this into the initial state, it would be a minus. And then this would be an amplitude for a minus quark to turn into a plus quark. But the rules for QCD with the gamma matrix in there tell us right away that helicity is conserved in all quark processes in QCD. So all these amplitudes are 0. But then there's an approximate helicity conservation that holds for gluons too, which is more amazing. So you go and compute a bunch of gluon amplitudes, and you find that, and you could also have quarks in there too. But if you have all the gluon helicities plus, all these plus, or exactly one is minus, you also get 0. So in particular, we want to know what these helicity configurations are for these 2 goes to 2 gluon amplitudes. And if they were all plus, you get 0. And if even one is minus, you get 0. So the A4 tree, or 0, and A4 minus plus 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 are 0. So there's only one non-zero amplitude, which, well, it's minus minus plus plus. Now sometimes we order these gluons according to color, and then you should also put in minus plus minus plus. So this approximate helicity conservation for gluons, it actually comes from a secret supersymmetry that tree-level QCD possesses. So QCD and n equals 1 super-Yang-Mills, that's a theory with a gluon and a gluino. And n equals 4 super-Yang-Mills, which has a gluon, 4 gluinos, and 6 scalars. They all produce the same gluon tree amplitudes. In other words, if you look at the coupling of gluons to quarks, or the coupling of gluons to gluinos, which might be drawn like this, you notice that because they're fermions, you have to make them in pairs. You started with some boson, you can't make one fermion that is half a unit of angular momentum. You got to make 2 fermions. So suppose I have a big blob with only gluons on the outside. And I didn't tell you what theory the gluons are coupling to. Oh, by the way, if I do n equals 4, it's 2. So now I come in here and I make some matter. But I'm going to insist that I'm only doing an n-gluon amplitude at tree level. Then I can't use these graphs because the fermions are not allowed to come out. The only thing I can do is eat them again, but if I eat them, now I've got a loop, and I'm doing a tree amplitude. So that proves this statement. that the pure glue amplitudes, they only have gluon interactions. They don't see the matter. So what's the big deal? The deal is that these theories have extra symmetries, and those symmetries can be applied to prove statements like the fact that all these are zero, that you can prove using supersymmetry. So the first non-zero thing you get is the amplitudes with two negative helicities. So often we write the helicities upstairs from the labels. So I might have an endpoint amplitude that has a bunch of positive helicities and only has two negative helicities, I and j. And this amplitude can be written down in terms of some quantities I haven't defined. So this is the Park-Taylor amplitude, although they wrote the cross-section version of it. And these quantities ij, they're spinor helicity variables, but up to some phases which don't matter when you square it. They're just square roots of the Mandelstam variables. So Sij is Ki plus Kj squared. For parton momenta, Ki and Kj. And because they're all taken to be massless, it's also the dot product. So this 4 is related to this n equals 4 super Yang-Mills. It's, anyway, this simple structure of these QCD tree amplitudes secretly there because they are the same as amplitudes in a highly supersymmetric theory. Any questions about that? Yep. Yeah. So the cases with quarks can be related by these same supersymmetry identities. And so if you want the, in fact, it's good you asked that. I think I was going to use one of those. So here's an amplitude which is thought of as helicity conserving because we're using this all outgoing convention. It looks like helicity flip, but when you cross this to the initial state, it's you've changed the momentum, so the helicity flips. So this would be plus goes to plus. So normally this would be non-zero, but if you put all plus helicities on it, you get 0. And furthermore, if you draw the same guy, let me do, I don't know, Q bar minus Q plus. And now I'm going to take one of these guys, I, and make it minus, but make all the rest plus. So that's the analog of this, except that I have a quark with a negative helicity and another antiquark. It has almost the same form. It has the same exact denominator as over here. Negative helicity here, and the one. So the formula is almost exactly the same, and there are supersymmetry ward identities which you can use to relate this one to this one. So there are lots of relations, and there's a hierarchy in how simple the answers are, and they get more complicated as you add more and more negative helicities. So they would not be quite as simple if you had, say, 6-point amplitude with 3 minus and 3 plus. That can be expressed in 2 or 3 terms instead of just one term like this one. So let me just do a kind of quick and dirty analysis of a unitarity cut with this, and then we'll probably be about done. So since A4, 0, with all plus or 1 minus is 0, and at NLO, we need A4, 1 interfered with A4, 0, we don't need to know these guys are actually very simple as far as one loop amplitudes go. They're like 1 or 2 terms and they have no logarithms or dialogues. But we can't do anything with them at NLO because they don't interfere with the corresponding tree because it vanishes. So what we do need for the gluon-gluon amplitude is we need A4, 1, 2 minus, 3 plus, 4 plus. And I should say that what we do is we take the A4s and exposing their color indices, we can decompose them. So these are supposed to be curly A's. We can decompose them into color-ordered amplitudes multiplied by color factors. And at one loop, the leading color factor is trace of A1 to A4. And then we have to sum over permutations of these indices. So these should really have some sigmas on them, but I'm running out of room. So I just want to say that you can divide things up according to certain orders of the orderings of these amplitudes. And so it's efficient to give the helicity labelings for things that are different permutations, but they're multiplying a cyclically invariant trace, and so you don't care about cyclic permutations. So I know I need one negative helicity, so by convention I put that one at the front. And I also know that I have parity in QCD. So if anything is true for one set of helicities, it's also true for the flipped set of helicities. So if I have 4 minuses or 3 minuses, I also get 0. So the only case I need is 2 minuses and 2 pluses. But I can divide that up into 2 cases according to where the 2 minuses are. And like I said, I can use the cyclic properties of some color traces to put one of them here. And then the other one could either be next to it in the ordering or across from it in the cyclic ordering. So this is sort of the job of the color helicity decomposed calculator to calculate these 2 things. So any questions about that? I know I didn't really explain all the intricacies of color ordering because I'm not going to go very far in this direction. So if this one is it negative, well then I would use this rule. So if I have three, okay, sorry. Do you mean 1 minus, 2 plus, 3 plus, 4 minus? Good question. What I say is that this one loop amplitude is the same as after I impose a inverse cyclic permutation, where I drop everything by 1 unit. So, no, sorry, yeah. So 1 minus becomes 4 minus, 2 minus becomes 1 minus, 3 becomes 2, 4 becomes 3. So I allow myself to use these relabelings to get the other cases. Yeah. So there are, there are 16 helicity configurations, which is 2 to the 4th. And they divide up into 1, 4, 6, 4, 1. And we just argued that all these are 0. And then this 6 splits up into 4 plus 2. 4 of them are cyclic rotations of minus, minus, plus, plus. And 2 of them are cyclic rotations of minus, plus, minus, plus, because that comes back into itself after only 2 rotations. So it turns out this one is simpler, and this one is slightly more complicated. So of course we'll look at the simpler, well actually it's 330. I think it's probably best if I just do that, start with that next time. This is a good place to stop.